Hi, today we're going to talk about subatomic particles, things found inside atoms. As a bit of a refresher, go ahead and hit the pause button and answer these questions now, if you'd like on your own. I'm going to get started. Electrons stuck randomly in the center of the mass, that's plum pudding from Thomson. Gold foil, that would be Rutherford's experiment, alpha particles, atoms are mostly empty space. And Dalton said that atoms of a given element have to be identical. And today we're actually going to blast some of these apart. But before I get too far into things, it's good to establish a bit of a baseline bit of information. If any of this is new information, do you go ahead and pause, take a second to write it down. This is the information that we are going to use moving forward. So I have these images to kind of get us started on our discussion. We have three different particles. They're all labeled carbon. Two are atoms, one's an ion, and you can see on the bottom we have a key for which particles are which. Obviously, we're going to pick this apart and see what information we can gather. Starting with the two on the right, this was labeled atom, and this was labeled ion. So we're going to take a second and use these keys to figure out what's the same and what's different. And looking at these, I can see same number of protons and neutrons for both, 6. And what's different is the number of electrons, where on the left we've got 6 electrons, and on the right we have 5 electrons. And remember that since we're calling this atom and ion, I guess we can kind of get a bit of a definition from that. An ion is a atom that has fewer or more electrons. I say fewer or more. This example is one of fewer, but of course we can add more. There are two types of ions, positive and negative, as I said, gain and lost. And those two ions have special names for just them. Cations, by definition, are positive. See what I did there? It's a cat. And anions are negative. So if we were to get a little bit more specific with our labeling, this would be an atom of carbon, and this would be a positive ion of carbon, or a carbon cation, if you will. The charge of this would be found by looking at the relative number of positives and negatives, protons and neutrons. So we have here 6 positives and 5 negatives. So we've got plus 6 minus 5 equals a total of positive 1. If we were to, this would be a carbon plus 1 ion. This atom over here has an equal number of pluses and minuses. You can see this electron here was the one that was lost. And that's going to serve as our basis of a definition for the word atom. By definition, atoms are electrically neutral, which means that the amount of protons is equal to the amount of electrons. The amount of neutrons doesn't really have much of an impact on the charge of the particle, since neutrons are, of course, neutral. But it is hypothetically possible to make two different atoms electrically neutral with the protons and electrons equal, but having a different number of neutrons present. This causes a bit of a discrepancy here. So now we've got a situation where these are both atoms, which has to do with the proton-electron numbers, but they have a different number of neutrons. So I think we can kind of define what carbon means by the 3 together. All 3 of these species had 6 protons in them. And we're going to use that information moving forward as a definition of what an element is. This atomic number is going to be equal to the number of protons in the nucleus. So moving forward, if we ever say carbon, carbon means 6 protons, period, the end. If it has 6 protons, it's carbon. If it doesn't, it's not. But this also calls into question. I don't know what happened to her. She panicked, though. What the difference in the number of neutrons means. So if we're going to count up, we have 8 neutrons over here, 6 neutrons over here. So how do we account for that? Well, going back to our previous table, the mass of these two particles would be roughly 14 and 12. Of course, the electrons have mass, but it's so negligible that we don't really add it up in considering the total mass of these particles. And when we have these two particles, two atoms of the same element that have different masses, we call that isotopes. So atoms of the same element, which means same number of protons, but a different mass, which is the sum of the protons and neutrons, which means by extension, obviously they need to have different numbers of neutrons to make that happen. In terms of naming these nuclides, which is the singular of isotope, we just say the name of the element. So carbon, you put a horizontal dash and the number 14. So this already is a bit of the code that comes out of here. When I say carbon, you know that means 6 protons, but when you see the number 14, you have to know that that is actually a sum. So your brain has to do a little bit of mental math. This is carbon 12. When it comes to representing these on paper, though, you don't always have to draw one of these atoms with these nuclei that are obviously way too large based on the Rutherford model. You can write this notation by just putting numbers around the element symbol, and luckily the reference table arrangement kind of helps you in that direction, helps you figure out. So we saw on the previous slide that this was your atomic number, sometimes abbreviated with the letter Z. And the number up on the top was the atomic mass. We're going to call it something a little bit different. When we're talking about an individual nuclide or isotope, that is the number that is the protons plus neutrons is going to be called the mass number. And so you kind of have to do a little bit of math here. So by taking the difference between these, if this is protons and this is protons plus neutrons, we have to subtract and say, yes, so this particle would have 18 neutrons and this particle would have 20 neutrons just through arithmetic. There is probably a question you're having of why doesn't the number up on the top of the periodic table match the number of either of these two isotopes, but I'm not going to get into that today. We're going to leave that for another day's discussion. So to sum things up, atoms being electrically neutral, you can kind of read everything that's there. They can become ions by either gaining or losing electrons. You can't change the number of protons in an atom to make an ion because that makes it a different element. And the charge, if at all, is present in the upper right-hand corner of that element symbol. So that first particle we saw on the right-hand side would be carbon plus. It has an atomic number, of course, so that means the bottom number is 6 because the capital C and the bottom number 6 mean the same thing. And then the mass number would go in the top left. And so for that ion, I believe the mass number was 12. I'm pretty sure. And so you can kind of like use this letter and all the things around it to communicate all this information about what that particle is, and without having to draw that particle, and it's great to all speak the same language. There might be a bit of a question in your mind of what goes in the bottom right, but don't forget that's where the subscript goes if there's ever more than one particle in or atom in your molecule or element in your molecule. So we kind of used all of our real estate when it comes to the space around that symbol. Thanks for watching.